Okay, this time we're going to be covering the ratio test. This is how it's defined. You have let your series AN be a series with non-zero terms. That's your first condition. And once you have that, these are your rules for the ratio test. AN will converge absolutely if the limit as n approaches infinity of a to the n plus 1 over an is less than 1. Your AN will diverge if your limit as n approaches infinity, an plus 1 over an is greater than 1, or it equals infinity, so it's greater than 1 or infinity. And then your third rule is the ratio test is inconclusive if the limit as n approaches infinity of an plus 1 over an equals 1. So I know that might be confusing, but basically what we're going to do is take our series, and for all the n's we're going to plug in n plus 1, and then divide by the original an, and if it's less than 1, it converges, if it's greater than 1, it diverges, and if it equals 1, it's inconclusive. So I hope that cleared it up a little bit. Let's start it off in example 1. This is what we're given, the series from 0 to infinity of negative 1 to the n times 2 to the n over n factorial. So the first step we're going to have to do, remember this is what we have to do with it. Here's what we're going to do. First we're going to turn it into a limit as n approaches infinity, and for each n we're going to plug in n plus 1, and then since it's a division problem we're going to multiply by the reciprocal of the original, giving us 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. You simplify that and you get, well, I'll walk you through the simplification. It's the first example. So here we go. 2 to the n plus 1 and 2 to the n cancel out. The 2 to the n's cancel out, leaving actually nothing but 2 right here on top. And the n plus 1's factorial and the n factorial cancel out. The n's also cancel out. You're left with just n plus 1 on the bottom. So whenever you see an n plus 1 and an n, that'll cancel out to just n plus 1. And a 2 to the n plus 1, or any other number to the n plus 1, and a other number to the n, will just cancel out to just that basic number. So here we're left with the limit as n approaches infinity of 2 over n plus 1. And when you plug in infinity, you just get 2 over infinity, which equals 0. And by definition, over here, it will converge absolutely if it's less than 1. And 0 is in fact less than 1, so it converges. Let's go over here to example 2. This is what we're given. The series from 1 to infinity of n times 3/4 to the n. Remember, we're going to start off the same way. We're going to plug in our n plus 1's and turn it into a limit. This time, since it's not a division, we're not going to multiply the reciprocal. We're just going to divide by the original. So you have the limit as n approaches infinity of n plus 1 times 3/4 to the n plus 1 over n times 3/4 to the n. Then you have, after simplifying that, you have the limit as n approaches infinity of 3n plus 3 over 4n, and by basic limit rule, that equals 3/4 when you plug in infinity. And since 3/4, again, is less than 1, it converges. So now, we're going to go over here to example 3. This time, this is what we're given. The series from 1 to infinity of n factorial over n times 3 to the n. We're going to do the same setup we have been, and since it's a division problem, we're going to multiply by the reciprocal as we add in our n plus 1's, and turning it into a limit again, of course. So we have the limit as n approaches infinity times n plus 1 factorial over n plus 1 times 3 to the n plus 1 times n 3 to the n over n factorial. After simplifying, it actually comes out very nicely, which you wouldn't expect after a big limit like that. But you simplify that and you get the limit as n approaches infinity of n over 3, and when you plug in infinity, you just get infinity over 3, which just equals infinity. And by definition, if your limit equals infinity right there, rule 2, it will diverge. So, example 3 diverges. And that's the basic concept behind the ratio test.